And welcome back to another LeetCode video. Today we're looking at LeetCode 2375. Construct smallest number from di string. So this is a medium problem, and let's approach this interview style. So we're going to read the problem description first, then check out the constraints. Check out the examples, come up with a solution, including space and runtime complexity, before we write a single line of code. Then we write the code, and then we use an example to step through our code with our mental debugger, and then we submit our code for judgment. Right. And well, if you wonder why I'm doing it this way, it's to kind of simulate the interview process, right? If you want to use LeetCode for interview practice, why not follow the systematic approach that you would during an interview? It's free practice. All right. So we're given a zero-indexed string pattern of length n. We're getting a pattern string that consists of the characters I, meaning increasing, and d, meaning decreasing. A zero-index string num of length n plus 1 is created using the following conditions. Num consists of the digits 1 to 9, where each digit is used at most once. If pattern at position I is equal to uppercase I, that means that the next number must be larger than the current number in nums, as we're building the string nums. If pattern at position I is uppercase D for decreasing, that means that the current number must be larger than the following number in nums. Return the lexicographically smallest possible string num that meets the condition. Aha, so we're getting a string that consists of increasing, decreasing commands, so to say, and we should construct a string that represents a number that follows that pattern, but we need to construct it in a way such that the resulting number is the smallest number that could be constructed by following the pattern. So presumably there are different numbers that you can construct using the same pattern, and we need to find the smallest. Cool. So now let's talk about constraints. I would ask the interviewer, well, is pattern ever going to have any other characters except for D and I? No. Are we guaranteed that we always receive a pattern, or can the pattern be empty or nil? Well, the answer is no. And of course, here in LeetCode, I have nobody to speak with, but I can read the constraints to get those answers. So, and indeed, pattern length is at least 1. We don't really care about the upper bound, by the way, because upper bounds make everything constant space and constant time, and that is really just a constraint that that LeetCode needs in order to run the code that we submit to it. Right? It's more like a practical constraint. But for the analysis of the problem, it's well, we're just going to ignore upper bounds here. And pattern consists of only letters I and cool. Alrighty. So now let's look at the first example here. So we have this pattern, and I'm just going to use this code area here for this example. So we have this pattern, and well, if I don't know how to solve this problem, I'm just going to play around with it just to see if I get some insight. So 0 is not in the range, so I can really use numbers 1 to 9. And I assume, since all can be used at most once, that automatically limits the pattern length as well. So actually in this problem, that is relevant for the space and time complexity analysis. Everything will just be constant. Anyway, so I'm diverging. So pattern I. So we could maybe say we start at pattern, I don't know. Maybe, so if I is 1, that means the current number must be smaller than the next number. That's what that means. So what's the smallest number? It would be 1, maybe. Maybe start at 1. But now we know the next number needs to be larger, and the one after as well. So we do 3, 4. Now the next number must be smaller, right? Because we now have 3 numbers. well, yeah. So the I means the next number needs to be larger. So we actually have to increase, well, we know that now the next number that we pick needs to be larger than 3. So it could be 4. But then we know that the number after 4 needs to be smaller because we have decreasing. Well, we cannot go to 3 simply because we've already used 3 up here. Right? But we could pick 5 and then 4. Then it would work. Okay, so that is interesting. 1, 2, 3 increasing, then 5, 4. Then we increase again, and the next higher number would be 6. That's the next highest number that's not taken. Right? The next number that is higher than 4 that is not taken, that would be 6. And now we need to find 3 decreasing numbers, but they would already all be taken. So if I can take 5, but if I change the 6 to a 7, I can then take the 6 or this one. However, I then can pick 5 as the next lowest. That works only when I previously picked the 7 and the 8 here. Then I can pick the 6. Now for the final D, well, I can pick 5. I can pick 6, but only if I picked 7 before. I can pick 7 only when I picked 8 before. And I can only pick 8 when I picked 9 before. Right? Yeah. So what I'm observing here now is that when numbers are in increasing order, I can just attach them. But whenever there's a decreasing number, I have to iterate backwards over the numbers that are picked to make sure that to increase them, right? So that happened when I was running into this decreasing and when I ran into this decreasing series here. So I wonder if that is a pattern that I can use. Well, and in fact, it is a pattern, right? So if I don't know if you see this, but if we have the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, if we were to always pick the current number at the current position, well, of the current index, right? If we just pick the number by index and we add it to our result nums, but when we run into a decreasing, we basically have to put them into like a LIFO. And once we reach an increasing number again, we will remove those elements from the LIFO or from the stack. So here with the DI, what that would mean is we put 1, 2, 3 into our result. Then we run into what do you say, a decreasing. So we put 4 in a stack. Then we add increasing again. So we get the 5, right? So now because it's increasing, it means we have to unravel the stack again. So we can put actually the 4 and the stack becomes empty. Okay, so now we're running into 3 Ds and we would pick 6, 7, 8 into and 9, right? Because it means the number after this index needs to be higher, so 9 goes into there as well. And then there's nothing else to do, but we still have the stack. However, if we now unravel the stack again, we will have 9, 8, 7, 6. So I think that is a solution that will work for us. And let's just see if it works with the second example. So we have the pattern DDD. And well, DDD would mean we pick 1, 2, 3, but we put it into a stack, and we have to pick a fourth one as well. Because The D just means after the first number comes a smaller number, right? That's how that works. So, and then we just unravel the stack and we get 4, 3, 2, 1. Yeah, so that would work here as well. And if we had only increasing numbers, you know, we would pick them in increasing order from 1 to 9, and that would also work. So, yes. So, the quick lesson here is go through the examples to identify patterns that you can use to exploit the problem. And I would now say, I think I now have a good idea how to solve this problem in linear time and with linear space, depending on how many elements we need to put in our stack. Are you happy with me implementing it? The interviewer will say, yes, this is amazing. You found the optimal solution. Of course, not going to tell me that, but I know. So now it's all about trying to write everything that I just said into some clean code, right? So we're going to have a result array. And in that array, we're going to put in numbers. We don't have to construct a string every time we make a further step, because creating a new string from an existing string is an O of n operation. So I will use an array. It's going to be O of n space, and then in the end, I'll just join all the array elements to one string. Also one O of n operation. Now we're going to need our little stack, and now we do a for loop while I in range length of pattern. And we saw that we need to be a little bit careful with, you know, when we have 3 items in our pattern, we have to produce 4 numbers. So I'm going to add +1 here. Right, so the default would be we're going to append the current number to our stack. And we're actually going to add I +1 because I starts at 0. So the number to add is, of course, that. So we're putting it into the stack. That's the default operation. Now, if pattern at position I is increasing, that means we are going to empty our stack in our result, right? And maybe I jumped here over one step. I don't know if you can see this, but if we by default add an element to the stack, let's say here with the 1, 2, 3, and we put 1 into the stack, but then we see, oh, it's an I. Okay, so that means we're going to put 1 into our result. And then we put 2 into our stack, but it's an I, so we're going to add 2 to our stack. It's just so that when we don't run into an I, that we don't empty the stack. So if we do, well, we will empty the stack while stack. We do run into I, we empty the stack. Result.append. And now we're going to take the, actually we could put this as ready. Append stack. Right. Cool. And now finally, well, at the very end, we also have to remember the second example where we had all elements in the stack. Well, we have to empty all elements back into the stack. You can either do it like so, or you could also say if or I is length of pattern. We could do it that way too, and then we'd save this little loop here. But maybe this is a little bit cleaner. Cool. So I'm fairly confident that this solution will work. And to make sure, I'm just going to walk through an example. And yeah, I'm just going to use our example that we have here. So we have this pattern. This is our pattern. And so what will happen, the first 3 entries, we will add the values 1, 2, 3 into the stack, but immediately pop them into the result array. So our result array will actually contain 1, 2, 3. Then we run into D. So we're adding now into the stack, we're adding 4. Goes into the stack, but we're not emptying the stack. Now we run into an I, so we're adding 5 to the stack, but we're also emptying a stack. And top of the stack is 5, bottom of the stack is 4. So that gets added as well to the result. Next, we're running into 3 times decreasing. So the values are 6, 7, and 8 that end up in the stack. And at the very end, we're going to put them into result in the reverse order. So that's going to be, I'm sorry, 6, 7, 8, and 9, since we are iterating over the length plus 1. And yeah, and now we just put the stack into result and it would give us the result. So I'm fairly confident that this will work. Let me just run the test cases to make sure I didn't overlook any obvious errors, and I did, right? So attention to detail would have helped me there. So result, stack, length, I'm not checking the colons, they're all in place. Yes, or pop probably needs braces. Yes, let's run the code. Was never closed, okay. Right. This is not good. This should not happen in an interview. String index out of range. Okay, that's aha. Yes. So in this case, this is actually yeah, I overlooked this. So this was definitely a mistake. So the problem here is that we run with I to length of pattern plus 1. And that means at one point we're trying to access one element further that doesn't exist anymore. And so what we can either do, if I is smaller than length of pattern, and this, or we could just say or here. And if it's equal to the length of the pattern, then we'll empty the stack as well. And then we can remove this down here as well. So now it passes the 2 test cases that we went through manually earlier. And yeah, and I now submit this to make sure that it passes all of the test cases that LeetCode has for us. Yes, very nice. So that's, I suppose, the most efficient solution to this problem. For one, because we need to iterate over all of the elements and pattern, and 2, because we need to create a result. But actually, you know, our n is actually 1, so it's constant because n is then, what was it? Because of this constraint down here, it's smaller or equal than 8. So everything is constant space and time. And yeah, that's it.